Hi everybody. Good morning.
Good morning.
I see a nice photo here. Have you ever looked at it? Does it belong to you? Oh my. It's a nice romantic picture. Take a look at it. I wish I could show it on the big screen. Anyway, let's get back to something more romantic. So, you know that your exam is coming, right? It's just barely a week away from now. And we discussed that the syllabus would be whatever we discussed up to week 4. Okay, I think week 4 is September 12th. Please check with your actual announcement in the Canvas to see how far we have gone. So today will be our class, and then we'll have one more class before one more week before the exam, and we plan to revise whatever we have learned so far in the next week, okay, so that you can have some opportunity to brush up your ideas and thoughts. And please, I highly recommend that you go through your syllabus and find out where you are seeing that there are some missing concepts, where you need some more explanations. So please bring those questions in the class so that we can discuss. Okay. So there was one question from one of your peers, and I want to address that question in front of everyone in the class. So you remember that when we discussed about Van de Graaff generator, so a Van de Graaff generator looks like the following. It has the motor inside it. The motor, it runs a belt, and the belt makes a friction with another material. Because of the friction, it creates some charges. The charge gets deposited on top of the metal, and the metal is connected with another big hollow sphere. So if we try to measure the voltage between the ground and somewhere so we are trying to draw the Van de Graaff, and we are also trying to draw a voltage probe where one probe is connected to the ground, and another probe is connected to either the air, like it's floating in the air, or it might get connected to the big sphere. So do you remember that what happens if I take this probe and put it somewhere away from this big sphere? Let's say just 2 inches apart. So does it pick up any signal?
Yes. Yes.
It does, right? So this means that actually there are electric fields all over the place. Those are imaginary lines, but the impact is real. And we also have seen, if I take this probe closer to the sphere, and even if I touch it, then it registers the maximum voltage. And for our case, we have seen that the maximum voltage goes up to 40 volts, something like that. All right, so you all can discover, right? If you take this further away, you will see a reduction of voltage. That means the electric field intensity is reducing over time. Now, what if I take this probe and put it inside the hollow sphere? So instead of having the probe floating in the air, let us say I take the probe inside the hollow sphere, but do not touch this probe to any of this physical object. What would happen? Would we register a voltage? Let me draw it here. So my sphere has some thickness, and it is hollow inside. You say that if I tap it on the body, I will register some voltage. What if I take it inside? Do I still see a voltage, or do I not?
No.
Yes. Everybody understands that? We will still see a voltage, right? Will the voltage increase, or will the voltage decrease? So, in case I touch the body from outside, let's say I get a voltage of 40 volt. What if I touch the probe, take the probe inside? Do I see a voltage greater than 40 volts? Less than 40 volts? It's the same. Right. And do you remember that what if I take some small metal balls, like some small aluminum balls, and put them inside the hollow sphere? How do they react? Do they start to jump around? No. What if I put those spheres outside? Do they react?
Yes.
They react. They start to fly around. Why? Because these balls will get some charge transferred from the big sphere, and if the big sphere has positive charge, then of course these guys, the small metal balls, they will also have positive charge, and they will start to repel each other. They will fly around. Okay. If I take these metal balls interior to this hollow sphere, then inside this hollow sphere there is no electric field, and that's why these balls won't react. Now the question is, you say that inside the metal balls there is no electric field, right? So let me write your definition one by one. So you say that inside metal hollow sphere there is no electric field. You also say that inside the hollow sphere voltage is pretty much 40 volt, right? So we know that voltage can be written as an integral summation of electric field over a distance. So if there are electric fields all over the place, I take my probe from far distance away, get it closer, I will integrate the entire electric field over the distance, and I'll get the voltage. So my question is, inside the field, inside the hollow sphere, there is no electric field. So if I put that zero electric field here, what should I get as the output?
Constant.
Pardon?
A constant.
A constant? Why do you think it's a constant? Why is it not zero?
And that's how integration works.
So it's actually a constant, but not a zero, right? You have taken a course on integration, right? So I believe that you know that when we integrate, we add a constant. Right? Do you know that why do we add a constant? Why do we add a constant?
The derivative of a constant is zero.
Very good. So integration is actually an inverse process of differentiation. Right? So let us say that we are trying to differentiate an electric field with respect to position x. So the differentiation of this guy, let's say this is the straight line, so I can write it as the following, that E equal to probably mx plus c, right? Where m is the slope and c is this y-intercept. So if you differentiate electric field with respect to the position, what do you get? dE dx would be equal to m, right? So this means if this guy changes the slope, we are going to see a change in its differentiation. But if this guy is going to move up and down, that means if this guy is going to change the C value, you shouldn't see a change in its differentiation, right? So this means that no matter what is the value of C, the differentiation would always be same, and differentiation would just depend on the slope. So if I say that I want to do the inverse process, that means instead of differentiation, now I want to go back to integration. That means somehow this C was missing from the differentiation process, right? This C just got vanished. So in integration, when I do the reverse process, I need to bring C back. Okay? So this is why when we integrate, we always add a constant here. And how do we determine the constant? In order to know the constant, we need to know some extra information. Okay? We call it boundary conditions. All right? So you understand that even if electric field is 0, let's say if electric field is 0, it doesn't necessarily mean that B is 0. B could be 0, but B may not be 0. What exactly would be the value of B depends on the boundary conditions. And what is the boundary? So let us say that we are trying to find out the voltage from, let's say, a distance which is far away. So let me write it infinite. Maybe I could write it minus infinite. To some distance, let's say we are trying to bring this probe from a far distance to the hollow sphere surface. So the radius of the surface is r. And we can write the total B as an integration of electric field from minus infinity to a distance of r. And then we can figure out that what is the corresponding voltage. Okay? Now, we know that if we bring this probe inside the hollow sphere, there is no electric field. Right? So, how do I plot this guy here? Can you see if there is any dusters over there? There is a duster over there. If you don't mind, please pass it to me. Thank you so much. Thank you. So let us try to draw the electric field for this guy. We know that if we go very far away, the electric field would be 0. So at a distance x which is very, very far away from the hollow sphere, I can say my electric field is 0. But as I get my probe closer to this hollow sphere, my electric field is going to go up, right? So I know also that electric field is proportional to kq by r square. Or let's say kq by d square, where d is the distance from the hollow sphere. So if I reduce my distance, E is going to increase according to 1 over d square. So that means how this shape would look like. If I bring this probe closer to the hollow sphere, let's say my hollow sphere is right here. Let's say this is my hollow sphere, okay? And the hollow sphere has a radius r. My probe was here. At this point, electric field is 0. As I bring this guy closer to the electric field, closer to the hollow sphere, this guy would increase, right? Would it increase in a straight line? How do you expect it to increase? Just look at this equation and tell me.
Inverse squared.
Inverse. So how should it look like? Like this or this? How should I draw it?
Curve inverse. Curve upwards.
Curves upwards. Right? Like this. Figure follows? That this is how the electric field should look like if I bring my probe from a very far distance away to somewhat closer to this hollow sphere. Okay. So, maybe when I reach the hollow sphere surface, my electric field is gonna go up by this much, right? Okay. So what if I bring my probe inside the hollow sphere? You said that inside the hollow sphere there is no electric field. So my electric field is gonna go down to 0, right? So this is my electric field inside the hollow sphere. Are you following what exactly is being drawn here? So what I do here again, I bring the electric field both outside and inside the hollow sphere. Outside the hollow sphere, if I go far away, electric field is 0. If I come closer, the electric field goes up. If I touch the surface of the hollow sphere, the electric field is maximum. But once I go inside the hollow sphere, electric field drops down to 0. So this is how the electric field would look like for Van de Graaff. Okay. So in order to find out the corresponding voltage, how we are going to calculate? We know that voltage is simply the integration of electric field over the entire space. So if I keep integrating all these curves, all the areas under these surfaces, these areas will determine what is the voltage. Okay? So everything under the curve would be the voltage. Now, if you keep integrating from minus infinity to some distance, your voltage is also going to go up, right?
Why are we integrating from negative infinity in the positive x direction?
It all depends. Like if you start from here and go up there, the voltage will just change its sign, right?
Right.
So don't worry about the sign, plus minus. Just look at the value for now. So if you keep integrating from here to all the way up to the close to the sphere's surface, you will keep integrating the areas. Right? So how do you expect the next guy would look like? If I integrate this curve over the entire space, how it would look like? Straight line? Or curved line? Or like this? What is your expectation? Again, consider the following. Electric field is kq by d square. So we are integrating electric field, that means we are integrating kq by d square over the space. So instead of d square, let me just write it x square to make things simpler. What will be the integration for this guy?
Negative straight line. Linear line.
So kq by 1 over x, right? This is how it looks like. Let's just ignore the sign. We're just focusing on the magnitude of it. So the voltage would again look like a curve which follows 1 over x, right? 1 over x looks like the following. Okay? So this curve, it follows the trend of 1 over x square. This curve follows the trend of 1 over x, right? Okay. So you keep integrating, you reach to the point where you touch the sphere surface, and now if you keep integrating to your further left, what do you get? Remember that when you integrate, you are just adding up all the areas that you have seen previously. Okay? So if you keep integrating to your left, your electric field is going to be 0. What is your integration value? Will it be 0?
Constant.
So it will be right flipped here, right? So that means the area is no longer increasing. To check whether you did it right, you can do the following. You take this voltage value, you take the profile, and you differentiate it. If you differentiate it and get the electric field profile, you know you are right. So how are you going to differentiate it? From this point, 0 point, up to the point of radius r of the hollow sphere, so this is the hollow sphere's radius, my voltage is constant. So if I differentiate the voltage, I should get the electric field. Electric field is the differentiation of voltage over the space, right? So if I differentiate it, I should get 0. It's a straight horizontal line. That's why electric field is 0. But once you get out of the hollow sphere, with the surface, and go away from that, you will see a differentiation, and the result of the differentiation would decrease, right? If you integrate, if you differentiate 1 over x, you will get 1 over x squared. So this is why electric field beyond the hollow sphere surface it decreases. So you know that inside the hollow sphere, despite there is no electric field, but there should be a voltage, right? And the voltage is actually clipped. Does it answer your question? So somebody asked this question. I wanted to discuss it in front of everyone in the class. So always remember that electric field could be 0, but voltage may not be 0. It could be clipped. All right. So we discussed about electric field, we discussed about voltage, and also we discussed about one more thing yesterday. It's about current and current density. We said that just like electric field can be integrated over space to get the voltage, you can integrate the current density over an area to get the total amount of current through a cable. So let's say we have a cable and we have electrons going up and down, and we want to know what is the current. So in order to know the current, we need to know the little current densities on each of these points. And when we integrate all these things over this entire area of the cable, we'll get the total current, right? Now, when people see this stuff, this thing, let me write one more stuff here. Resistance is defined as the ratio between voltage and current. So we can expand it further by saying that voltage is an integration of electric field over space, and current is an integration of current density over surface. Take it one step further, we can also say that current density can be written as the conductivity of the material. So instead of J, current density, we can write it as sigma E. Sigma stands for the conductivity of the material, and S stands for the surface. So if you do the surface integral of current, if you do the line integral of electric field, you should get the resistance R. Right? Now, let us say that we have a voltage source. It's very simple. AC voltage source. We have a voltage source, we have a resistance, and maybe we have some light, LED light in our circuit. And we want to know how much resistance the LED light offers. What is the resistance of this light? How we are going to calculate it? So we know the resistance of this guy, let's say this is R1. But this resistance, let's say this is RL. L stands for like load or light. We know the value of R1, but we don't know the value of Rm. We know the value of voltage. So in order to know the value of Rm, we can do the following. We can find the current in this circuit, and the current, let's say the current is I. So this is I, right? And I would be a ratio between voltage and the total resistance, RL plus R1. So if we can find out the current, then the resistance would be the voltage drop across this LED, which is I multiplied by so let's try the following. The VL, that is the voltage across this LED, is going to be I multiplied by the resistance RL. Right? So from these two equations, you can figure out that what is the corresponding value of resistance RL that you see on this LED. Right? Now in this entire circuit, we have never used, you follow that how this resistance can be figured out, right? If you know the voltage, if you do not know the resistance, you can still figure it out by looking at the corresponding current and figuring out that what the value of resistance RL would be. Now in this entire solution process, we have never used any idea from what we have learned in this course. Right? We have not looked into the electric field distributions. We have not looked into the current density and integrated over its entire space. These are all very simple equations, right? Very simple equations. And we have studied this when you have taken a course on DC circuit, right? Something like that. So why we are going from simple analysis to a very head-twisting analysis? Right? This already gives us a headache. So what's going on? Like, why we make things difficult? We should make things simpler. Right? So there must be a purpose why we are taking into account of all these nitty-gritty details. Why a simple voltage and current ratio would give us everything. There must be a reason for that. So let us see how an LED may look like from interior. So what we see here is the LED, and we are also seeing a little bit of the interior of the LED. Okay? So let's look at the first guy. So our left-hand side shows an LED, and the right-hand side shows what is going on inside those LED. So inside the LED, we have a flat piece of semiconductor, and the semiconductor consists of two types of junctions, P-type material and N-type material, and the junction between them. So you say that you have a course on, you did a course on semiconductor, right? All of you have done it?
We're not experts. We're just now.
I understand. But is there anybody who have heard about the word semiconductor for the first time?
Like Tuesday. We started.
Yes, go ahead.
Oh no!
So is it
we started it on Tuesday. We started diodes on Tuesday.
Oh, you're taking the course this semester?
Yes. Yes.
I see.
We're not. We don't really get
I
it.
see. Okay. Like you have not passed that course, right?
Yeah.
So treat it as if
We have no knowledge. We have no knowledge.
So there
Assume
is
we know
still a
nothing.
chance that you could fail
Yes.
in that course to come back.
Yes.
Understood. So that helps you. So let me try to express that as if nobody knows about it. Okay? I'll try to make things as simple as possible. It's not actually simple.
We're full of kindergarten.
Okay, so well, Well, let's forget about P and N junction. Like I cannot explain the entire stuff in just a few minutes. But how about the following? Let us say that somewhere here there is a loose connections of wires, and the connection just got it got disconnected. Okay, two wires, they were previously connected. Now it got disconnected. So because of the disconnections, the entire room goes out of electricity, and you want to make the connections again one more time, right? So what do?
Splice it
You
together.
take those. Pardon?
Splice it together.
Yes, splice it together, right? So you take those two disconnected cables and bring them together. Maybe you twist it. Right? That's exactly how it works. If you twist two cables, again you will see electricity to flow from one guy to other, right? Okay. So when you twist it, you know that there is no chemical connections between those two pairs of wires, right? They are physically touching each other, but there is no chemical connections. There is no chemical bond between them, right? So if there is no chemical bond, this means those junctions are the weakest link of your entire circuit. Okay? And why those are weakest link? Simply because no bond is attaching them to each other. If let's say you take one aluminum piece of wire and another iron piece of wire. So one is aluminum, one is iron. So both are metal. You connect them together by twisting. You know that all of them have very different properties, material properties. Material property means they have very different conductivity. Why? Because aluminum, it is made of one kind of atoms. The atomic structure is one for aluminum. The atomic structure of iron is completely different. So they have very different conductivity. They have very different density of electrons. Okay. So this means if you bring them together, if you just connect them by twisting, yeah, if you supply a very large amount of current, maybe those little difference between aluminum and iron won't matter to you. But what if instead of supplying a very big current, let's say you are supplying a very small amount of current, like nanoampere current. A nanoampere current, if you try to supply it through two different metals, then of course it depends on what are the properties, material properties at the interface of those two metals. Okay. So inside an LED, even if you do not know about semiconductor, think about it that we are bringing two different materials close to each other and make a junction. Okay. So since all these things are very small, in fact, the stuff that I show you here, can you make it guess like how big this small rectangular stuff is?
Nanometers.
Nanometers?
Yeah.
No, I mean I'm talking about this guy that you see here. It's a nanometer.
The chip?
Yeah, the chip.
Yeah. I think it's
10 nanometer.
10 nanometers.
10 nanometer. Is it because I talked about nanometers? So
No.
just tell me, like,
Yeah.
imagine
No,
you
that's
are a
the
kindergarten
transistor, right?
student, okay?
Well, like consumer SOCs are at 3 nanometer now, so you would
No,
assume,
guys,
you would assume
you are-
it's not that complex.
Give me 1 second. So you are going too far. Maybe you already know a lot of stuff. So imagine that you are a kindergarten student. If I ask a kindergarten student, what is the size? They have probably seen LED.
1 inch.
1 inch is too big.
That's all kindergarten.
It's not wrong.
So an LED is probably this size, right? This little size. So maybe it's few centimeters. And if you take out the dome shape inside of it, you will see a rectangular piece of device. That rectangular piece is probably few millimeters. So this guy that I show you here, the red yellow guy with the square shape, that's probably few millimeters, not more than that. But this guy is not actually the actual device. It's actually plastic. Okay? And the reason why they put plastic is to just protect those devices. The real device, which is underneath it, is actually much more smaller. Okay? very, very small. So all the stuff that you see outside, it's the protections. It's like those Amazon boxes. The boxes comes bigger. Inside it's nothing. Like I often wonder why they put this big box just to purchase some small stuff. And maybe the reason is the packaging reason is they want to give the protections. Okay? I mean, they don't want to lose money and they don't want to lose customers. So in a similar way, when you show this stuff is few millimeters, but inside the actual device is very, very small. Maybe it's a micron. Okay? Nanometer is too small. It's micron. And LED, if you look at the inside of the device, it's micron. So if you take two materials of micrometer size and bring them together, if two materials have two different properties, then it really depends like how you are actually joining them together. In case of a very large wire, like when we are trying to twist those two wires, the size of the wire is millimeter, right? So in case of millimeter wire, you can really twist it without thinking too much. But if it is a micrometer, you cannot just twist it. Okay? The twisting may not give you the right result. Because now, the chemical bond between them matters very, very crucially. So in case of a very small structure like this, when you break it inside and look into the micrometer structure, you cannot just think about the whole structure as an aggregate form. You have to take care of the fact that each of these structures is very delicate. So we have to take care of what is going on inside each of these structures. So if I break it even further and try to see what is going on inside, we will see the following. So this is the stuff that we talked about, and which is few millimeter in shape. And few millimeter means it's actually the Amazon packet. You break apart this Amazon packet, go further inside. Inside the actual device is few microns, and now we are seeing a few microns device. This is few microns. From here to there, this is few microns. This guy is few millimeter. So how much difference between the size of this guy and this package? Almost 1,000 times. 1,000 times smaller is the actual die. And look at the actual die. It has two different materials. The green guy and the blue guy. And how do you make the connections between them is very important. Okay? You cannot simply twist it. You cannot twist two micron size device. Is it possible that if you take these two devices, let's say this is one device, it's called P-type device, this is called N-type device. Can you just take two P-type device and N-type device and just put them together like this? Do you think it will work?
I doubt it's that simple with that.
It's not that simple, right? Of course it is not that simple. So how come fixing a wire of few millimeter size is very simple, like as simple as twisting it. But how come this guy is very difficult to make them work and make them connect? Because if you want to make them connect, you need to make sure that they have atomic bonds from one material to another material. Without that atomic bond, it will never work. Okay? So, in order to make this guy work, we need to take care of each and every single details. For instance, we need to know what are the electric fields at each and every single point of this, how they are chemically getting connected. And in order to know the total value of the current going through, we need to take care of each and every single details, like what we discussed here. That we want to know what are the electric fields at each point, what are the current density at each point, and only then we will know that how the device is going to perform. Okay? So, the bottom line of all this discussion is that things become much more complex once we scale things down. In case of millimeter or maybe centimeter, things are much more simpler. This is why when you studied the network theory, you studied the DC circuits, things were much simpler because everything was big in size. But things become very complex once you start to bring things down, make it very small. So at that point of time, you need to take care of that how exactly the electric field is there in each and every single point, and how you are going to calculate for the current from one guy to another guy. And all the time, you need to use these kind of equations, like electric field and the integration of electric field over the entire space. To give you one more idea about it, so let us say I ask you to fill up a jug of water. And how we do it? It's very simple. You just grab some water in a glass and you just pour it. And gravity will do the rest of the work for it, right? You pour the glass. Because of the gravity, all the water is going to enter into the other jar. It's that simple. What if I tell you the following? So let's say I have like a very small pipe, a very small straw, maybe 0.1 millimeter. And I ask you to put water to that small straw. So you try to put some water to that small straw. Do you think it will be very easy to just inject water to this small straw? Why? Previously you did it, right? You had a big jug, you just put water because of the gravity, all the water fill in. Now I ask you to do the same stuff through a small straw. You cannot do it. What's going wrong? Like, what else is there that prevents you from doing this? What other physics is working here?
Surface tension.
Surface tension, very good. What else?
Can you repeat
the question?
Yeah, please.
So the scenario is the following: that I want to transfer some water from one pot to another pot through a small straw, small pipe. And how am I going to do that? Can I just pour the water to the small straw? Do I expect that the straw will just convey the water to the other pot, or something else will be there? Is the question clear now?
You got to soften it out.
Right. So you have to do some special techniques, right? Like siphoning. So if I make it even more smaller, like instead of 0.1 millimeter, maybe it's 1 micrometer, would siphoning work?
Oh, not.
Yeah. Why not?
You couldn't get enough air through the.
So you should realize that each time we are narrowing down the scale of the device, we are facing new and new physics. Those physics were not previously there, and now all of a sudden, those physics have to be taken care of. For instance, if you make this like 1 millimeter, maybe surface tension is the thing that you need to take care of. If you make it even more narrow, then apart from the surface tension, some more physics will be there. Maybe there are some atomic frictions that you need to take care of. So every time we go smaller, we need to think about new kind of phenomena that we have previously not encountered. So in a similar way that what we are teaching here, the electric fields and the current densities, everything would be essentials once you go further down inside. Okay? So this is why it may look very complex, but this is actually very much necessary. Like, you of course do not want to be an electrician who fix this wires, right, in your entire life. You want to do stuff like that much complex, which will add real value to people. And this is why we are studying electric fields and the current densities. So things have some significance and why we are trying to do this. Okay. All right, guys. So I think we discussed a little bit about the significance of why we are trying to do this. I don't want to pressure you too much today. So from the next week, as I said, that please try to bring as much question as possible from the first 4 weeks of lectures. We'll try to cover them in the class. And of course, we can discuss in person, we can discuss in the office hours, but I actually prefer to discuss it in front of everyone. Even if some of you already know about it, I think it's a good idea to again go through these ideas and differentiate. Thank you.